Hello students, in previous session we have seen the resemblance between the bar magnet and solenoid. The magnetic field produced by the bar magnet was same as the magnetic field produced by the solenoid. Now we'll see the two important terms related to magnet, which are pole strength and magnetic dipole moment M. Okay. So what is meant by pole strength? Here we have seen the bar magnet is the magnet which is in the shape of a rod or which is in a shape of bar, which is called as a bar magnet. They are having the two poles, first which is directed towards the south direction, we are calling it as the south pole, and which is directed towards the north, which is we are calling it as a north pole. The south pole will have a charge which is a negative charge, and pole strength of that charge is given by minus Qm, and this is given by plus Qm. So we'll understand what is pole strength. Pole strength is the strength of the magnetic pole to attract the magnetic material towards itself. It is pole strength is the strength of the magnetic pole to attract the magnetic material towards itself. It is called as a pole strength. S will have the minus Qm is its pole strength, and N pole will have a plus Qm as its pole strength. Okay. Now the distance between these two poles we will be calling it as a 2L. So this pole we are showing over here some distance these are not, we are not showing it to the corners, it will be inward to the total length. So this is called the length between these two poles, we are calling it as a magnetic length. We are calling it as a magnetic length, and this length of the magnet, it is your geographic length. It is your geographic length, and there is a relation between the magnetic length and your geographic length. Magnetic length is equal to 5/6 times your geographic length. Magnetic length is equal to 5/6 times your geographic length. So the distance between these two poles, which we will be calling as a magnetic length, and this is your geographic length, which is 5/6 times your geographic length. Okay, this is related to the pole strength. Now one more term which we have already used in the previous solenoid equation, which is magnetic dipole moment. Magnetic dipole moment, which is given by this, which is denoted by M. This is M into 2L. So M is the one of the pole strength, right? Pole strength is given by M. So one of the pole strength, that is the pole strength of the one of the pole and the distance between these two poles, right? The magnetic length of the material, which we will be calling it as a magnetic dipole moment. Pole strength of one of the pole and the 2L is the distance between these two poles, that is a magnetic length. We will be calling it as a magnetic dipole moment. Magnetic dipole moment is your vector quantity. Pole strength is your scalar quantity. This is your ampere meter is the SI unit of pole strength, and ampere meter square is the SI unit of your magnetic dipole moment. Now we are going to consider 5 cases actually, which will show you the relation between the pole strength, magnetic dipole moment. We are considering the special cases for that, and there are 5 cases which we are going to consider, and we are going to make a table of that so that it will be easier for you to understand it and recall it at the time of examination. Okay. So you can give a heading as pole strength and magnetic dipole moment special cases. Pole strength and magnetic dipole moment special cases. Make 4 columns. First column here we are going to consider what is your special case. Then here we are going to draw a figure to show how that magnet looks. then we are going to have the effect when we have changed the change its shape. Then what will be the effect on the pole strength? Is it going to increase? It is going to decrease. And if it is decreasing, then how much it is decreasing? And formula for as your pole strength changes, your magnetic moment is going to be, the magnetic dipole moment is going to be changed. So what will be its new formula? New formula for magnetic dipole moment. Okay. These are the headings which I have given. Make 4 columns. Okay. So first case here, which we are going to see, if we cut your bar magnet, this is my bar magnet. If I cut a bar magnet, what happens if I cut a bar magnet? We will be getting a 2 bar magnet. Okay. Here, please try to understand that we never get a unipolar magnet. Magnet will not exist with a single pole. It is unlike the electric dipole. Okay. It is always present in it. So, when you cut a bar magnet, it will become N pole and this will become S pole and NS pole. Its strength will be weaker than this. If you again cut this bar magnet, again it will have N and S. And if you go on cutting it to a smaller and smaller length, it is going to have the 2 separate bar magnet with dipoles. Okay. Now, if so, first case is bar magnet cut into 2 equal pieces, that is length is half. You can cut it in 2 ways. Na? You can change its width also and you can change its length also. Now first case which we are going to consider is you cut it into half its length. Second case will be if you cut into the width wise. Okay. Now if this is my bar magnet, this is my N, this is my S pole, ulta. S and N, minus M, plus M, and the distance between these two is obvious 2L. Now if we cut it into 2 parts, then it will be L, L, this will be a minus M, plus M, minus M, plus M. Okay, you have cut it with its length, right? Now, pole strength, here your pole strength remain unchanged. Your pole strength remain unchanged. But what will be your magnetic dipole moment? The first formula for magnetic dipole moment for this figure, it is M into 2L. Right. Now, the second formula for this will be M is not going to change, but your length is going to be half. So, it will become M by 2. That means my M dash, that is new magnetic moment, dipole moment will be M by 2. So, it becomes half. It becomes half, that is M dash is equal to M by 2, which is your first case. Now, second case. In second case, bar magnet cut into half, width is half. Now here I have cut it length. Now I am going to cut it with its width. This is my S, this is my N, negative M, positive M. If I cut its width, then it will become length will be same. So it is minus M by 2 now, and it will be minus M by 2, which is plus M by 2 and plus M by 2. Length will be same over here. Length will be same over here. Now pole strength is going to be half, which we have shown in a figure. So pole strength what you are going to write over here becomes half. Pole strength becomes half. Now here, if I have not cut it for the fresh pace, m is equal to 2L. Now m dash will be what? M by 2, right? Because I have cut it into the width wise. So my pole strength becomes half, and into 2L same. So it is become again m by 2. That means again it is becoming half. So magnetic dipole moment becomes half if we cut a magnet widthwise into half of its length. Okay. Third case. If I bend the magnetic into a semicircle, bent into semicircle. This is my magnet. I have bent it into the semicircle. What will be its figure? Like this. Right. Now again this will be my negative, this will be my positive. Distance between these two will be L, 2L. Okay. Now pole strength will become same. It is not going to change or affect your pole strength over here. So it is remain same. Are you agree with this? Now here, when I have not bent it, at that time my m is equal to m into 2L, right? But when I have bent it, then it will become m dash is equal to m into 2r. This is my r radius, so it will become m into 2r. So what will be the value of r over here? So first we will calculate the value of r. So 2L is equal to pi r. When we have considered a whole circle, at that time it will be 2 pi r. Here we have considered a semicircle, half circle. So 2L is equal to pi r. So what will be my r over here? R will be 2L upon pi. Put this value in this equation, m dash. So again my m dash is equal to m 2 into 2L by pi. M into 2 into 2L by pi. So what quantity we have changed? So m dash is equal to, what I can say, this m into 2 by pi. Into 2 by pi, because this value has changed if we compare with this equation. So it becomes 2 by pi times. You can say my new m dash, that is magnetic dipole moment. If I bend my bar magnet into half circle, then it will become m dash is equal to m 2 by pi. That means it is going to change with value 2 by pi. Two more cases which we are supposed to consider. I will rub it down. You please copy it down first. Bent into a semicircle. Finish with copying this. Now, if two bar magnets, two identical bar, this is a fourth case, when two identical bar magnet join perpendicular, I will write like this, perpendicular to each other. Perpendicular to each other. Now here we are consider a two bar magnet. This is my first bar magnet. This is my second bar magnet. It is perpendicular to each other with its center over here. Again this is S, N, minus M, plus M. Here S, N, minus M, plus M. Now, Is your pole strength going to change? No, it will remain unchanged. Now, we want to have the magnetic dipole moment. Now, in this case, magnetic dipole moment, your M will be under root M1 square plus M2 square. So, it will become 2M square. So, M will come out is root 2M. Now, it is M dash. Your M dash will be root 2M. This is the fourth case when two bar magnets are perpendicular to each other. Pole strength is not going to change. It will remain same. And the last case where two poles are inclined with each other. We'll write over here. Fifth case, write down when two bar magnets are inclined at an angle theta. Now, this is my first bar magnet. The first bar magnet. This is my second bar magnet. And these two bar magnets are inclined to each other. Now, magnetic moment will be in this direction. M, the angle between these two is theta. This angle with a magnetic moment with this is phi. Again, this is my S pole. This is my N pole. Again, this is S pole. Again, this is N pole. The magnetic field which is produced by this is M1, and magnetic field produced by this bar magnet will be your M2. Okay, this is the figure. Two bar magnets are inclined with each other at an angle theta. Your magnetic pole strength will remain same. It is not going to affect. So, here you can write remain unchanged. It is remain unchanged. Now, we want to see what will be its new magnetic dipole moment. Here, dipole moment M dash can be given as it is M1 square plus M2 square plus 2M1 M2 cos theta. And this is your new magnetic moment, that is new magnetic dipole moment. M1 is the magnetic moment because of this bar. This is M2 is because of this bar magnet, and it is the theta is the angle between which these two bar magnet. Now phi is the angle with the resultant magnetic moment with the first bar magnet, that tan phi. How you will give a tan phi? It is given by M2 sin theta upon M1 plus M2 cos theta. M1 plus M2 cos theta. Okay, these are the special cases regarding the pole strength and magnetic dipole moment in a special case. Okay, these will be help you out in solving the numericals. Now, we will try to solve the numericals based on the theory which we have covered. So, write down the first numerical. A thin bar magnet of length 2L is bent at a midpoint. If this is a magnet, we have bent it in a midpoint, so that angle between them is 60 degree. That means they are forming a equilateral triangle, right? Find a new length of the magnet. Find the new length of the magnet. try to draw a diagram so that you can understand what you are supposed to calculate. The length of the bar magnet is 12 and it is bent into a half, and so that the angle between these two magnets will become 60 degree, which they have given in your numerical. Okay, so how it will look? We are solving the first numerical, right? So this is my bar magnet, right? So it is making an angle of 60 degree over here. Will not like that. We'll consider a single line for a bar magnet. Okay. Now, when we have bent it, this length will be L. This length will be L, because total length they have given as a 12. What we want, if we mark it as A, B and C, that means we want to find out what they want us to calculate. They want us to calculate a new length of a magnet. That means we want to have this distance AC. What is this distance? So what if we consider O over here, your AC is equal to AO plus OC. This total angle is 60, so it will be theta by 2. That will be a 30. So if you can calculate a sine 30, that is 60 by 2, and L, you will get a value of this AO, same will be value of OC. You add it, right? So here what you can write, L sine theta by 2 plus L sine theta by 2. Here you directly write, you can directly write as a 30-30. See, this angle is 60. I have drawn a perpendicular bisector to this angle. So this angle is 30. You can write it down L sine 30, right? So this is L sine 60 by 2 plus L sine 60 by 2, L sine 30 plus L sine 30, which is my 2L sine 30, which is 2L into half, which is nothing but my L, which is nothing but my L. Finished with doing this? Second numerical. Length of a magnetized steel wire is L. Length of a magnetized steel wire is L. And its magnetic moment is M, capital M. It is bent in a shape of L. L shape. The wire is bent in a shape of L, with two sides equal. Normally we have the L like this, but they want us to have the same shape of both the sides. What will be the new magnetic moment? What will be the new magnetic moment? What is the formula for magnetic moment? It is M, that is a pole strength, into the distance, right? So first we'll try to draw a figure and then we'll try to visualize how it will look. Second numerical. Now, right, length of the magnetized steel wire is L. Now it will become L by 2 and this will be L by 2, right? So this will be L by root 2. M is your pole strength. Suppose M is your pole strength of each pole. Magnetic moment M is equal to M into L. Here they have mentioned that the length is L. So you don't take it to L, it is L. But here, what is your L, effective L, which I want, because this wire is bent, no? So the distance between magnetic moment and the distance between two poles will be L by root 2, right? So you have to consider this distance between these two poles from here to here. So it will become what? L by 2 bracket square plus L by 2 bracket square, which is L by root 2, right? How I have calculated this? Pythagoras you can use. So now new magnetic moment M dash will be what? M into L by root 2. Right? What they want? They want a new magnetic moment. So this is not your answer. Your answer will be, first my magnetic moment was when it is not bent. At that time it is M. Now it become M dash. Now if you want to substitute it, it will be M by root 2. M by root 2. Here when you bend it, your magnetic, that pole strength is not going to change. Only the magnetic moment will change, which is M by root 2. Okay, have you finished with this? Now we'll take one more numerical. It is based on solenoid. Write down the numerical. A closed wound solenoid of 800 turns. An area of cross section 2.5 into 10 raised to 4 meter square carries a current of 3 ampere. Explain sense in which solenoid acts like a bar magnet. What is its associated magnetic moment? What will be its associated magnetic moment? First we will write a given data. It's very easy. So it's N, which they have mentioned is 800 tons. Area vector is given as 2.5 into 10 raised to 4 meter square, and current I is 3 ampere. Right? What they want us to calculate? M. Magnetic moment is NIA. Put the value. N is 800. I is 3. 2.5 into 10 raised to 4. So it is round about 0.6 joule per Tesla. Okay. Now you can write down below this. This magnetic moment acts along the axis of a solenoid in a direction related to the sense of flow of current. Write down. Acts along the axis of a solenoid in a direction related to the sense of flow of current according to right hand screw rule. According to right hand screw rule. So these are the numericals based on this. Now in the next topic we will be going towards the dipole in a uniform magnetic field. We have seen this magnetic field line which we have covered. The magnetic field lines will give you the direction of the magnetic field, but that will give you the approximate value of the magnetic field. So if you want to have the correct value, then you have to go for the torque, and for torque of the compass needle, and comparing the deflecting torque and your restoring torque, you can have the magnetic field over there. That part which we are going to see in the next lecture. Thank you.